Okay, so we have our reverse time algorithm, and what we'd like to do now is implement an improvement that will allow us to interpolate. So why don't we go ahead and take our reverse time component here, and let's take a look at what we've got. Let's go back to reverse time component.h, and we'll scroll down and we'll see that we have a reverse running time. And what we really want, though, is a left reverse running time and a right reverse running time. So let's do that. Let's do a float left reverse running time and float right reverse running time. And this will keep track of the left and right frames that will be to the left and right of our current running time that we will want to interpolate between. Okay, so what we're going to do now is I'd like to go back to our reverse time component, and when we come down to where we're reversing time here, we'll see that we've got some code here that basically will result in setting the actor location, rotation, setting its, getting its static mesh component, setting the linear and angular velocity. I'd like to refactor this into its own little function. So why don't we go ahead and create a function for this? And what we're going to do is we're going to basically give ourselves something that we can call right here, that we can just pass in the location, rotation, and angular and linear velocities. So let's go to reverse time component.h, and down here at the bottom, let's make a function void, and let's call it set actor variables, and it's going to take a actor for the owner actor. The owner actor is going to be the owner of this component, and so we can pass that in as a pointer. Let's go ahead and pass in an f vector for the location, a f rotator for rotation. Let's do a f vector for linear velocity, and let's call it linear vel for velocity, and an f vector angular vel for angular velocity. Okay, and we can go ahead and implement this. We can stick this in reverse time component.cpp, and we can define it. Okay, and so in order to define this, we're going to simply take we're going to go back up here, and where we get all this information. In fact, we don't really even need the actor for the owner actor. We can simply get it in the function. So I'm going to take that out. And this function will only take a location, rotation, linear, and angular velocity. And what I'm going to do is I'm going to take this bit here, and I'm going to just simply copy it and delete it and paste it in here into our function. And instead of location, I'm going to, instead of setting actor location to the tail get value location, I'm simply going to pass in location here. And it looks like I've accidentally deleted my function name, set actor variables. So I'm going to go ahead and put that back. Okay, so for set actor location, I'm going to pass location. For set actor rotation, we'll pass in rotation. And finally, for set physics linear velocity, I'm going to pass in linear vel. And for set physics angular velocity, I'll pass in angular vel, like so. And so now all we need to do is call set actor variables up here. So we can simply call it here. And instead of location, well, all we need to do is get the tail get value dot location, and we can pass in the rest. But we're not really going to do that. We're going to actually change our algorithm a little bit. And so how are we going to change the algorithm? Well, what we want to do is let's go ahead and just take all of this and delete it. And we're going to implement our method that involves interpolation. So we have our running time, and we have our left reverse running time and right reverse running time. Let's go back, and up here while we're recording data, up at the beginning of tick component, if not reversing time, we're storing data. The first thing I want to do is set running time to 0. And also I want to set left reverse running time to 0 and right reverse running time also to 0. Because every time we lift up off of the right mouse button, we stop reversing time and we start recording data, and we can reset these to 0. That way, whenever we start reversing time, they're going to be reset and ready to be set again. So every frame while we're reversing time, we're going to take running time and add on delta time to this. This is an count of the amount of time that's passing each frame as we're reversing time. Okay, next what we're going to do is we're going to get our left and our right nodes, and we're going to set those equal to the tail, and then we're going to set the right equal to the tail and the left equal to the previous node of the tail. So we're going to say auto right equals stored frames. Remember, stored frames is the double linked list. We're going to get tail, and we're going to say auto left is equal to the right get previous node. And I'm going to set the left running time equal to the right running time plus the right, we're going to get value and get that delta time for the right. And this is actually left reverse running time, which is kind of a long name. I'd kind of like it to be a little shorter, so I'm going to call this left running time and right running time. We're going to have to go back up where we used it up here and call this left running time and right running time. Okay, so we've got our left and right, and we set them equal to the very end of the node and the one to the left of that, the tail and the tail's previous node. And we're setting left running time equal to the right running time plus that delta time. And so right running time is not changing yet. Now what we need to do is we need to say while running time is greater than left running time. If that's the case, then we need to move left and right over by 1 incrementally until left and right are on the left and right of our running time. So each frame, as we, each iteration of the while loop, if running time is greater, what we're going to do is we're going to say right running time plus equals the right get value delta time. So we're moving the right over by 1. We're also going to say the right equals the left. We're moving the right node. We're designating that right node variable to be the one next to it, the left one. We're also going to say left running time plus equals left get value delta time. And then we're going to take the left and move that one over left by 1. So left equals left get previous node. Okay, so then we're going to say auto tail. We're going to get the tail. It's going to be equal to stored frames dot get tail. So that's the end of. So that's the end. Basically, the right node used to be the tail, but then we moved it over by 1. Now we need to get that tail, and we want to remove that tail. And so we're going to remove the tail, and we're going to take our recorded time. We're going to say minus equals tail get value and get its delta time. So we're subtracting that off of our recorded time. That's, remember, a recording of the time of all the stored frames. So since we're removing the tail, we need to remove the tail's delta time. Okay, now we can actually remove that. So we can say stored frames dot remove node, and we can remove that tail. Now, every time we do this, we need to check to see if we're going to be out of data. So if the left is the head of the node, if the head of the list, then we're removing the very last one and we'll be out of data. So we can say if left equals, and we can say stored frames dot get head, that's the head of the list. If the left and the head are the same, then we're out of data, so we can simply say b out of data equals true. Okay, so that takes care of marching our left and right over until running time is no longer greater than left running time. If running time is no longer greater than left running time, that means left running time is greater, and it's left running time, the left node has a frame package that corresponds to being on the left of running time in data, and the right one will be on the right. So now we have the left and right, which we can interpolate between. So what we can say is after this while loop has finished, we can say now left and right surround running time. And we can say if, we can just check to make sure if running time is less than or equal to left running time, and we can say running time is greater than or equal to right running time. This is just double checking to make sure that running time is in between these two nodes. Well, now we can do our interpolation. Now we need to figure out a fraction between 0 and 1 that represents how far along we are between the left and right nodes. And that's where we need to interpolate. So we can say float dt. This is going to be basically our running time minus right running time. And that's going to be where we are at currently in our running time minus the right node's running time. And this will give us the difference. This will be the time from the right running time to the current time. So it's somewhere between right and left. Now the interval is left running time minus right running time. This is the total amount of time between the left and right nodes. Between those two frame packages, this is that delta time. Okay, and then we can say float fraction is equal to dt divided by interval. And this gives us the amount of time as a fraction between 0 and 1 between the left and right times. Now we can simply do our interpolation. So we're going to say f vector interpolation for the location, interpoloc, equals fmath, and we can use the v interpto. This interpolates between two vectors. Now the first is going to be the location for the right node. Remember, we're going from right to left. So we're going to say right get value dot location, and that'll be the beginning, or from the perspective of this function, the current node, and the target node is going to be the left location. So we're going to say left get value location, and then we need a delta time, and of course the interp speed is going to multiply, but our delta time, we're simply going to use our fraction. And for our interp speed, we're just going to use 1.0 f or 1.f, and that way it won't affect anything, because remember, this returns the distance between the current and the target times our fraction, basically. And so that's what we're going to get for our interpolation. We're going to do the same thing for interprotation. F-rotator interprotation, or ROT, equals Fmath R interp2. And we're just going to say right get value rotation. And then the target is the right get value left get value rotation, and it's going to be fraction for delta time and 1.f for the interp speed. Now we're going to do the same thing for linear and angular velocities. So what we're going to do is we're going to take this vector line, we're going to copy it twice, and for this one we're going to say interp lin vel for linear velocity, and it's going to go from the right, not location, but linear velocity, to the left linear velocity, and it's going to use and 1.0. And then for the last one, this is going to be interp angular ang vel for angular velocity, and it's going to be the right get value angular velocity to the left get value angular velocity, and that gives us the interpolation location, rotation, velocity, angular and linear velocities. This should be linear velocity. So we're basically taking advantage of these v-interp2 and r-interp2 functions, only we're sort of using it a little differently. We're passing in the left, the right and the left frame package locations, or rotations, or linear angular velocities, whatever the values are. We're going from the right to the left, and then we're just passing in for delta time that fraction, which is basically the fraction of time that's passed from the right to the left as we are reversing time. So finally, what we can do is we can call set actor variables, that function we just made, and pass in our interp in variables. It's going to be the location, so interp location, interp rotation, interp lin vel, and interp ang vel for angular and linear velocities. Okay, so now we should be interpolating and setting those values. So why don't we go ahead and compile this, and let's see how this works in action, and then we'll analyze and take a look at our results. Okay, so we've compiled. Now we're back in the editor. I'm going to hit play. I'm going to cause some mayhem, and then I'm going to reverse time. And everything seems to be working fine. Now, let's go ahead and take a look at something that we get as a bonus for interpolating. So since we're interpolating between frames, we should get a smooth transition no matter where we are between frames, which means if we're reversing time, we can scale our running time by a factor and make our time reversal slower or faster. For example, let's take our running time, and instead of plus equals delta time, why don't we plus equals delta time times 0.5f, and this way our delta time will be scaled by half, so when we're reversing time will reverse, but it will do so half as fast. So let's reverse time, and there we have it. It looks like time is going a little bit slowly, more slowly, while we're reversing time. And it's still smooth, so that looks good. And we can go basically as slow as we want to. I'm going to scale it by 0.1, so this way when we're reversing time it's 10% of the speed. And let's give this a try. Okay, now let's reverse time. And there you'll see it's going very slowly, but it's still smooth. If you look really closely, the movement is very smooth as we're interpolating in between frames that we've stored. And you'll see at the top left, recorded time is going very, very slowly. So because we are interpolating, we get a smooth transition between those frames, and it doesn't matter that we don't have the data for the exact time, because all we need is data in between, basically on either side of our delta time, of our running time, sorry, rather, and that will give us 2 points to interpolate between, which will give us exactly where we should be for that frame. So that's a kind of a cool bonus of interpolating, is you get to have this slow motion, and you can allow yourself to basically set the speed yourself. So there you have it. There is a reverse time algorithm for you, and it's not very difficult to implement. It takes a little bit of thinking to conceptualize it, but there you have it. That is one way to achieve time reversal without being too inefficient, and also without having to rely on the assumption that delta time remains constant. In fact, delta time can vary as much as you want it to, and you'll still get robust, consistent results. So there is, this will conclude this little mini-series on time reversal. If you want, you can expand upon this by, maybe setting the main character's position. You can probably, if you want, you can store the mouse input, or even the control rotation if you want to. So that's, I leave that as an exercise up to you. All you need to do is store that data in the frame package and save it and update it as you're recording and as you're reversing time. All right, so I hope you enjoyed this video. If you did, please consider liking and subscribing and sharing and all that stuff. This will be posted to Druid Mechanics Facebook page, so if you like it there, go ahead and like the page first of all, and then share it. Show your game development buddies, and if anyone might benefit from a reverse time mechanic, go ahead and share it with them. All right, Druid Mechanics signing out.